Yeah,
Great, thank you. Welcome everyone to the Thursday, September 12th, 2024 edition of the HamSCIence Zoom call. We talk about a lot of different things related to the ionosphere, the magnetosphere, and aeronomy, I guess is the right term. Today we've got a very fortunate to have Jason Dare here, and I'm sure he's itching to get going on his talk, talking about the big magnetic storm we had about 4 months ago, almost, yeah. So Jason, you want to take it away? We'll let you rip.
All right, let me share here. Can everyone hear all right? And does this look all right?
We need full screen. There you go. Good job.
All right. So yeah, I'm gonna basically talk about some work that I did with Colonel Diana Laux, Colonel Stephen Hamilton at West Point, and super talented cadet who I should probably give the lion's share of the credit to, Joanna Halfhill. And basically, we have a bunch of different local instruments at West Point and a research group that focuses on the magnetosphere and the ionosphere and how they couple together. And we have some particular focus on how it impacts GPS scintillation, for example, and radio wave blackouts and the like. And so I just, prepared this yesterday. It's going to be a little bit off the cuff. I haven't practiced or honed it, but it's sort of just a nice fun talk. I will give maybe a larger fraction than usual at these into the magnetospheric causes of storm time impacts, because that's sort of a lot of my background from before West Point. The pictures on this just show some nice local images of aurora taken at West Point. And so you can see there's both green and sort of this pinkish red aurora. So a very intense event, and West Point is at mid-latitude. So of course, this was a crazy intense G5 geomagnetic storm. All right, so as I'm sure most people here know, all of this storm time stuff is really driven originally by structures in the solar winds that emerge from the sun's surface. You get sort of weak magnetically bound plasma in local regions of the sun's surface. We see these as sunspots, but then they have a lot of structure over top of them. You'll get these things called prominences. Maybe some of you saw prominences during the eclipse, and they're very, very large, and they can basically, it's a loop of magnetically bound plasma, and it can get stretched out and twisted and become unstable and then emerge from the surface of the sun as a coronal mass ejection. Usually this is a result of magnetic reconnection happening at the boundaries of the footprints. And so we also see extreme flares that emerge whenever you have a CME eruption, or at least I should be clear, for most CME eruptions, there are exceptions. But this time...
from the.
Sorry, go ahead.
No, keep going, Jason.
Okay. Yeah, so we got some very intense X-class flares during this storm associated with, I think it was 7 different coronal mass ejections. This is a solar synoptic plot. This was taken straight from SWPC, so I did not produce this. But basically, they draw these nice images of the sun's surface and where you see the different magnetic structuring. So there's a lot of different, complicated structures on here I'm not going to go into in detail, but the plus and minus signs are basically the regions where the magnetic field are coming out of the sun's surface or going back into the sun's surface. And of particular note for this storm, if you zoom in on this really warped, complicated region over here, this is active region 3664, which was responsible for a whole train of CMEs that erupted and impacted the Earth's magnetopause and caused the storm. These different numbers here just tell you, I think it's likelihoods of flares of different intensities. So C class, M class, X class, P class. All right. And we can return to any of the slides if someone wants to ask some other question later, or jump right in while I'm talking, no problem. I'm not going to go through this whole timeline in detail, but basically starting on May 7th and 8th, it became clear that these two complicated active regions were merging, and the polarity of 3664 ended up dominating, and we got gigahertz range radio bursts, and they were, of course, detected on the day side because that's just pure, light, right? So it's not going to reach over to the night side. There's no complicated magnetosphere dynamics there. But then on May 8th, we got the first coronal mass ejection. And then within the span of hours and then into the next day, we got a total of 7 coronal mass ejections, many of them associated with extremely intense flares. Of course, the flares also conditioned the ionosphere, D region and E region, on the day side before any of the storm time impacts even started. And then this image right here is showing just 3664 in a more realistic image. And then after May 9th, 3664 rotated away from the Earth. All right, so this is much closer to home. We're now looking at Discover satellite data taken at the L1 Lagrange point in front of the Earth. So this is basically our stable orbit in front of the Earth that serves as a monitor for what's coming in from the solar wind. Strictly speaking, the data has been propagated from L1 to the magnetopause where it causes all the action. All right, so this image on the left is from the magnetometer, and this is the total magnetic field, and then Bx, By, Bz. It's all as a function of time. Units are nanoteslas. Over here, we have Faraday cup data. So this is much more about the particles, right? In particular, I think you want to look at the top 3 panels, the density, the temperature, and the speed of the protons. Of course, it's proton dominated, so we can, for simplicity, ignore these other minor ion species. And the red markers indicate each of the CME impacts. And so I said there were 7 CMEs, and so you might wonder why there are only 4 impacts. And the main reason is that 3 CMEs merged on their way to the Earth in transit from the Sun. And so you can see this first coronal mass ejection here between between the 2 red lines is much more highly structured and intense than the subsequent ones. Right? Another feature I want to draw your attention to is, so BZ, this red region here, is shaded for when the magnetic field is pointed opposite direction to the Earth. And this is what causes magnetic reconnection and allows the plasma in, right? So when BZ is pointed in the same direction as the Earth, you're not going to get nearly as intense driving of the magnetosphere and ionosphere. All right, one more point before we move on. I gave the starting point for the CMEs. Of course, each CME isn't completely full until the next one, so there's some end point. And the way you can see that most easily, I think, is by looking at, like, for example, density and speed, and I guess density and speed kind of show it most nicely, where you'll see prior to the first CME, this is just sort of the solar winds, quiescent solar wind, right? Then you've got a CME. Right here, towards the end, right before the second red line, you get a way dip back to ordinary, proton velocities for the solar wind. Vx rises up to the normal value. Density drops back to the normal value. So we think that's the end of the first CME. I should have shaded it, but this is still a work in progress. Second CME, you can also see a fairly clear return of multiple fields at the same time, about, a third to a half of the way through. And then the third and fourth are much less intense, less structured, and it's just really hard, I think, to say what the boundaries of those are. All right, so what is a geomagnetic storm? Here's where I'm going to get into a lot of nitty-gritty magnetosphere physics. We have this set of ground magnetometers located all around the Earth near the equator, and we can take the average of the magnetic field, the horizontal component of the magnetic field, at those regions, average them together, and get this basically like an index that indicates how intense our storm is. And for a storm, you have a fairly typical sequence of events, and our storm also had this sequence. You have this initial phase where DST, which is, you can think the average northward pointing component of the magnetic field, you get it increasing at first. This is really where the CME impacts, compresses the magnetopause, and therefore increases the Z-directed magnetic field as measured at the Earth by pushing all those magnetic field lines closer. Then after a certain amount of time, you get this sequence of reconnection events and an injection of lots of plasma into the magnetotail. That's going to get wrapped up in this dawn to dusk circulating current around the Earth. I'll show nicer pictures of that later. But that, if you just use right-hand rule, you end up seeing that you're going to get a strong negative depression in the equatorial magnetic fields. And this is the main phase of the storm. This is really where the ring current's becoming very intense and where you have the vast majority of the intense auroral and, radio wave propagation interference. And then the recovery phase is just sort of where the ring current relaxes through a variety of means. You get particles precipitating from the radiation belt, and so you lose some of the most energetic population. Some of the particles get lost to the solar wind. Some of them collide with neutrals and exchange charge, so that you end up with basically a very hot neutral particle, and your ring current decays. This storm had a minimum DST of -412. Just for reference, the famous 2003 Halloween storm had one of like -422, so comparable intensity there. And a typical storm lasts, I don't know, something like days to a week on average. All right, so we're going to focus a little bit on some magnetosphere stuff. This is going to be fairly technical, and I'm going to try to just focus on the most important stuff, but stop me if it gets a little bit tedious. So we're looking at 3 different views of the magnetosphere here. This one on the left, I think, is the most sort of obvious, similar to what most people have seen. Solar wind is coming in from the left, and then it gets diverted around our magnetopause, which is a sheet of current separating the solar wind's plasma and magnetic field from the Earth's plasma and magnetic field. These, connected arrows here, these are the magnetic field lines. Of course, the day side is compressed by the solar wind and the night side is stretched. You also have an embedded current sheet in the night side where most of the plasma is located. And this is really the sheet of current that ends up getting diverted in all different ways into the ring current and into currents along the magnetic field lines that cause energetic particles to precipitate down into the ionosphere and produce plasma and optical emissions. So in particular on this picture, what we're going to see is like when the CME compresses the day side, what's happening is that this current that's pointing towards you on the day side of the Earth, that's going to get pushed inwards towards the Earth. And so these northward pointing field lines also get pointed towards the Earth. And so that's why you get that initial storm commencement where the DST goes positive. Okay. Then you have a whole sequence of events where the plasma comes around the night side of the magnetosphere, it gets injected into the tail, and then we'll talk a little bit more about the ring current using this picture over to the right here. All right, so the picture on the right is showing you a top-down view. Sun is still to the left, Earth is this little tiny dot in the center. Here you can see this tail current from dawn to dusk that you could see here, right, pointing towards you. And if you go a little bit pretty close to the Earth, you get this ring current, right? And so what's happening is that a lot of this plasma that was injected into the night side from the solar wind gets entrained in this ring current and the ring current becomes very, very intense. And again, if you use right-hand rule, for those who've taken a Physics 2 class or something, you'll see you wrap your right hand around this current, you'll see that the magnetic field is going to be pointing southward, so through the page in this picture on the right, and that's what causes this very massive drop. All right. Okay, and so I guess the last thing I want to stress, just for some understanding of the closure of all these currents, right? Currents have to be closed. I want to show how the magnetopause current connects up with the current sheet. So now this picture in the center, we're looking from the tail of the Earth into the board is going to be both the Earth and then the sun way further in. And we're sort of embedded in this current sheet. So dawn to dusk is now to the left, where here it was coming out of the page towards you. The magnetic field lines are pointing out of the page on the bottom and into the page on the top, which corresponds to the right here, and then back to the left on top. And this current sheet, the main point I wanted to show is this magnetopause current that is flowing away from you above and below the magnetosphere. It then connects back up into the page of that left picture, produces the crosstail current sheet, and then that crosstail current sheet splits again. So this is the magnetopause current wrapping the whole way around the Earth. And then that's the source for this current sheet that flows from dawn to dusk. All right. And dawn to dusk instead of dusk to dawn is really just because we happen to have a planet where the North Pole is, where the field lines are directed how they are. They could have gone the opposite way, and all the arrows would be flipped around. All right. So that was a little bit hairy, and I'm sure I didn't do a perfect job of explaining all the details, but we can revisit it if necessary. I'm just trying to give all the context for what's driving the ionospheric stuff. All right, so on the day side, after this compression of the magnetopause, you get this process called magnetic reconnection. So first, focus on this picture on the left. When you have magnetic field lines, that's the red and blue lines here, that are oppositely directed, when they flow towards each other from above and below, then they cancel out at the center and end up flowing towards the sides. And you'll notice that the things that flowed in had completely distinct populations, but the things that are flowing off to the left and right, they have mixed populations now. So this is how the solar wind ends up leaking into the Earth, even though the magnetopause resists that cross-field transport of particles and energy. All right, so here on the right, we're looking at this two-stage Dungy cycle where you have basically day-side reconnection. I tried to embed these tiny versions of the GIF or GIF, however you want to say it, into this picture so that you can see on the day side what's happening is the blue is the solar wind energy coming in, and then this is what leads to the flow of the magnetic field lines and plasma around the Earth over to the night side, right? So things mix, and then you get flow over the poles, and then this ends up, one after one, compressing the night side, and then you get another reconnection event back here where you have oppositely directed field lines. They reconnect from above and below flows, and then the flows come outwards in both directions to the left and right. So the one that's going off to the right is just going to stream into space. We don't really care about it. The one that's streaming to the left, this is the plasma that's going to get caught up in that current in the magnetotail and eventually end up forming a very strong ring current. All right, this is just one more nice image to kind of show how these different currents relate. We have a whole zoo of current systems. This picture on the left, again, just shows, I think, kind of a nicer three-dimensional view of what I was trying to show before, which is the crosstail current, and then how that connects to form these two layers of magnetopause current that surround the Earth and sort of protect us from inflow from the solar wind. This picture over here, just focus on the blue. The blue is the ring current. And this is very, very close to the Earth. So this entire picture would be embedded in the open region here. So a bunch of particles are going to flow in from the tail towards the Earth, and eventually they're going to get real close because they're very energetic. And they're going to form this ring current, very intense, and that's really the source of most of the storm time dynamics. There's one more type of current that happens, and this is what was responsible for the auroras. These are called Birkeland currents or field-aligned currents, very famous for those who are interested in auroras. These were basically, we figured out that there are diversions of this crosstail current that end up, instead of moving from dawn to dusk, you get flows along the magnetic field lines into the ionosphere and then back out. And so current systems have to close. So the only place left for it to close is through the ionosphere. And so it's that flow of current through the ionosphere that leads to a bunch of collisions of particles from space with our atmosphere that produce the optical emissions. All right, so for the storm, basically you get this sequence of events. I've skipped the middle panel because it's not terribly important. The first sequence is the tail current strengthens, right? First, you just get an injection from the tail. So that sort of darker blue crosstail current gets much more intense. Then after a while, in fact, after these purple currents intensify and you get auroras, that would be the B panel. The C panel is most of it ends up eventually getting caught up in this ring current, which is now super, super intense. And again, ignore some of these smaller, weirder currents. There's a whole zoo of currents that could take like 10 hours to discuss. So, all right. One more comment on the substorm aspect of this, because we also got these auroral signatures and pictures. This is a picture of these little packets of plasma streaming in from the tail towards the Earth. This is a Center for Geospace Storms simulation from some colleagues at Johns Hopkins. So these stream in towards the Earth from the night side, and these are what end up getting in the way of the crosstail current and leading to these field-aligned currents into the ionosphere. It was flowing across. Now there's this little bubble of plasma in the way, so it can't make it through. And so it ends up flowing into the ionosphere and then producing that so-called auroral electrojet current that you see as, you know, green optical emissions. All right. Let's see here. And these substorms, by the way, are much shorter duration events. They're like, you know, they typically happen several times daily and last a few hours instead of lasting, you know, days to a week. But the reason that I discuss both is both of them happened here. We got both a G5 intense geomagnetic storm, and then embedded within that was a super substorm, which is a very, very intense substorm. And we saw it at mid-latitudes, which is, of course, super rare. Usually you expect them at high latitudes, right? So here's a nice picture of the optical, right? This is the substorm seen from over the US, and West Point's going to be somewhere around here, right? So we saw very, very intense auroras. Usually this oval is, you know, over Canada and Alaska. So it's because those field lines got so pushed towards the Earth on the night side that they went to lower latitudes. Their footprints were at lower latitudes. So I'll just to show this because it's interesting, right? Normally it would have been on these field lines here, but this time it got way further because of all that plasma injected, and so it ended up much closer to the Earth, and the footprints are at lower latitudes, right? So that's why we saw it at West Point instead of just in Fairbanks, Alaska or something. All right. So these are just some nice images of the precipitation. This is from the DMSP satellite. This is publicly available data, so if you ever have some interesting event, you can just look this up. This is from May 8th and 9th, so this is before the storm started. This is just to give you a baseline. And this is a polar orbiting satellite that measures all different optical waves, and I just picked lower band hybrid. You could have picked others. It shows very similar patterns. It's not super important for what I'm trying to show. But, okay, 8th and 9th. Then let's look at the 10th and 11th. Okay, first focus on the 10th at the left. Not a whole lot happening. But then around like 1700 UT, you're going to see things really start to get intense here. And then on the right, it's pretty much crazy intense auroras all day and extending to much lower latitudes than usual. All right, so here's a nice image of some indices, right? We have all different indices. These are like, you know, like if you're focusing on the science of earthquakes, you have the Richter scale. You have all different global indices for weather things, right? Hurricane categories, for example. These are very similar things where you average over a bunch of magnetometers in the right regions, and that sort of tells you what the global state of the ionosphere is doing at that time. So we already discussed the DST. This top panel here is showing you the so-called SMR, supermag ring current. It's just a much more resolved DST, finer time scale, you know, time resolution, and more magnetometers. Okay, so here again, you see at around the time of this first red line, which is the first CME, shortly after you get a compression of the magnetopause and the SMR rises, right? And then here's the decay of the ring current for our event. It lasts, you know, sometime into the 11th. I should mention these different shadings of gray and white. Dark gray is nighttime. White is, you know, noon. And then the lighter grays are dawn and dusk. So we're looking at time here starting somewhere on late on the 9th into the 13th. All right. And just for reference for later plots where this is going to be more important, the black dashed and solid lines, those are flares. Flares aren't going to really show anything on this plot, but it'll become important later. Red, just like on the Discover satellite, this is the CMEs. Blue is the start of the main phase of the storm. This third blue line is the end of that decay phase and the start of the recovery phase. All right. This second panel here is showing you upper and lower boundaries of the auroral oval. So it's very similar to this. It's just these are high latitude magnetometers. So this is really showing you more like what the aurora is doing. This is a measure of the electrojet that came from those field-lined currents instead of the ring current. And so since this is currents flowing in the ionosphere instead of out in space, they're going to be way larger magnitudes, right? These are in the thousands instead of the hundreds. So you can see, basically, once this first CME impacts, all of these indices go crazy, right? And then they start to decay as the ring currents also decaying. This third one I'll just skip over in the interest of time. We can revisit any of this if someone's interested. All right, so from Jen Gannon, and I should mention, Jen Gannon is from CPI at UC Boulder, or sorry, CU Boulder, and she provided us with a magnetometer, which is a little bit interesting because, like, you know, she is one of the people who this storm we're considering naming it after her because she died very shortly before the storm started. This is the CPI magnetometer that we got from Jen Gannon, and it's located in Atlas, which is not West Point, but it's close enough for good measure. The field line oscillations that we see are going to be somewhat similar to the ones we're going to see at West Point. So, but this is still one of our local-ish measurements to characterize the storm. And again, you can see this clear coincidence of the crazy oscillations of these magnetic field lines, right? This is BX, BY, BZ, and then on the right is horizontal, BZ, and then total, okay? But basically, they're all showing the same thing. The magnetic field lines are jiggling like crazy because these bubbles have arrived near the Earth and are oscillating those field lines. All right, so in particular, it's very clear the first CME is where all the chaos starts. All right, so now we're going to get way more into stuff that probably y'all are much more familiar with than I am. So I've mostly done magnetospheric physics and magnetosphere-ionosphere coupling. Only more recently, like in the past 2 or 3 years, have I delved into some of the radio wave propagation through the ionosphere stuff. So now we're really digging into that. I'm sure you all know the ionosphere is these vertically striated layers of plasma as you go up in altitude through the Earth, and that because of the differences between day side, where it's being produced by sunlight, and nighttime, where it's, you know, recombining but doesn't have quite enough time to disappear, you get different patterns on the day side and night side for how these regions look as a function of altitude. But basically, the ionosphere exists because sunlight shines on the day side, rips apart our atmosphere, and produces plasma layers. And on the night side, we get sort of the more magnetospheric relevant things, where you get those precipitation of particles along the field line currents. And what they do is they also collide with both neutrals in our atmosphere and local plasma that still exists from sweeping around from the day side. And that precipitation from space both produces more plasma and produces optical emissions. All right, and so one of the main things that we focus on at West Point is ionospheric scintillation. So this is these very high frequency waves coming from the GPS satellite. It's like L1 and L2 band, and they stream down through the ionosphere. They're sufficiently high frequency that they just punch right through, right? And in general, GPS satellite positioning works because you have some, I guess let's focus on this picture on the left here. This is straight from Wikipedia. You have some number of satellites in their orbits over the Earth, and from any given location like the blue dot here, different satellites become visible as they come over the horizon. And we combine basically the travel times of all of these different signals as they reach the GPS receiver, and we can figure out positioning, right? More satellites is better, of course, but there's this additional subtlety where this whole idea relies on it just being a vacuum, right? The travel times and the distances, the conversion factor is the speed of light, because radio waves travel at the speed of light. But when there's an ionosphere in the way, it modifies that propagation, as you all know. And so the GPS receiver doesn't know what's in the way, right? So you're going to get positioning errors as a result of that radio wave propagation being refracted and diffracted as it goes through the ionosphere. Okay, this picture on the right here, this just shows you a given satellite, the radio wave propagation to the receiver, and then this slab here from 50 kilometers to 1,000, this is our simplified ionosphere. There's this thing called slant tech, which is basically the total electron content, the total number of electrons along this slab, which is the intersection of that radio wave with the entire ionospheric slab as it travels through. Now, for science reasons, the GPS satellites, they're going in all different orbits and have all different slants to them. It's very convenient for us to pick some point where there's like a maximum ionospheric density and flatten those out so that they're, you know, altitude tech, so that we can produce maps instead of these sort of random arbitrary paths through the ionosphere. So that's called vertical tech. So I'm going to show some plots of slant tech and vertical tech from the satellite radio waves that reached our local receivers at West Point that are their cases receivers provided by Orion Space. All right, so here's our GPS receiver data. At the top, you just see that ring current again with the red lines and so on, right? By the way, these plots were back and forth between me and my student Joanna Halfhill, and she's really the one that is responsible for this just, beautifully informative plot. So all the credit to her there. But here you see right when this first CME impacts and the storm starts, this top panel again is the ring current just for reference. All these things at the bottom here are different GPS related signals. So this second panel here is the vertical tech. Okay, so you can see again, right when the storm starts, super intense increase in plasma density that is encountered by this radio wave as it propagates through the ionosphere. The third panel is the rate of change of tech as a function of time. And basically what you see is a lot of spikes starting with rapid changes in plasma density, again, coincident with the start of this storm. And the bottom is, this is a GPS scintillation index. Basically, it's, much like DST is supposed to be a one number representation of how strong the ring current is. This is supposed to be a one number indicator of how strong the scintillation of these GPS signals is. And I want to point out a couple of things here. First of all, you can see the scintillation's quite intense. It sort of starts to become intense as the storm begins. And then actually it becomes more intense, I think, during the recovery phase of the storm. And we're still a little bit puzzled about why that is. So any thoughts there would be helpful. Another very interesting thing that I noticed was at this flare that arrived at the Earth before the storm even started, we get super, super intense scintillation on one particular satellite. By the way, I forgot to mention, all the different colors here are indexed to distinct satellites. I should have said that. All right. This is just a different way of representing the scintillation. What you're seeing here is at the center is the location of our receiver. And this is an azimuth elevation plot. So basically, the center point is pointed directly up into the atmosphere, so the purely vertical. And then this circle at the boundary, that's the horizon in all directions, right? And what you're seeing with these traces here, each trace is the trace of the path of one of the GPS satellites as it passes overhead. You'll see we have less coverage to the north. And the colors here, this is top panel's slant tech, second panel is vertical tech, and the third panel is that rate of change of tech. Really, they're all showing a similar thing, which is that on the 10th of May, you really start to get very intense signatures on all of these. Now, not on every single satellite, right? Some of the satellites might just pass overhead and miss the plasma entirely. And this is a work in progress, so we're still trying to figure out which satellites were scintillating and which weren't, and what the geometry and timing of all that is. This is just the entire trace over the day, and for all the satellites. But you can see the 10th of May, things start to get pretty crazy. 11th, pretty crazy in rate of change, but it looks like the rate of change is mostly leading to a decrease of plasma density. So I think what's happening there is the ionosphere has lifted now, and much of that plasma is flowing back out into space to help relax the ring current again with this cold plasma. Right? It's cold from the perspective of space. And then the 12th and the 13th, we're sort of back to relatively normal. I mean, there's still a couple satellites that are scintillating pretty heavily, but relatively normal conditions. It's really, I think, starkest on the rate of change plots. All right. And finally, we've got a personal space weather station that was provided by Nathaniel. And this is just the Doppler plots for that station. Now, I should mention, the station, of course, is located at West Point, but these modifications of the ionosphere are not at West Point, right? The radio waves are bouncing off, what is it? I think it's from Colorado, is that right? Maybe Nathaniel can interject here.
Yeah, we're assuming that it's from WWV
Yeah.
in Colorado. As long as you're on, those are all 10 megahertz plots. Yes, probably
Yeah.
WWV in Colorado.
Yeah, perfect. Okay, so basically this is halfway between there and here, roughly, right? But it's still interesting because it's a local measurement that we took, and I think probably particularly interesting to this community. And this is the 10 megahertz band. We have all the different bands. I have lots of these plots. I just included a few to kind of highlight the main point. And so top left corners on the 9th, this is sort of like relatively normal, right? On the 10th, still like not terribly crazy, right? The storm started sometime around 1300 or so UTC. But you can see, yeah, the Doppler's quite disturbed, right, compared to normal. There's a lot of jiggling up and down of the ionosphere compared to a normal day. And then on the 11th, right, when we're well into the main phase of the storm, total blackout. At least that's my interpretation. I think that's what's going on here. And then on the 12th, you're still getting a decent bit of blackout, quite a bit of Doppler spread, a little bit of recovery. And by the way, we went up to the 14th. It still wasn't recovered yet back to kind of the normal day pattern. All right. Last slide here. So two different pictures of some auroras taken at West Point. Most of these were taken by cadets and colleagues. And we also have an RX-88, or I should say Colonel Hamilton has an RX-88. And so that has, I think, many more frequencies that we can look at, and we can get some more tech information from that. I can go a little bit more into the relation between storms and substorms, or, these bubbles, they cause both the field-aligned currents that cause the electrojet, right, the substorm, and they also inject particles into the ring current to cause the storm. And that's why storms and substorms are so related. We can certainly get into that more if anyone's interested in that aspect. It's a bit hard to cover it in such a brief time when I wanted to eventually get to some of the radio stuff. Right-hand rule we can go through for any of the positive and negative field deviations if we want. It's not terribly interesting, maybe. It's the intensity of those magnetic field changes that really matters. Oh, and I guess I did have some questions about these plots in terms of, I would like to get something like these stitched into this. So I'm not really sure. All I did was download from the PSWS website. Colonel Hamilton and I have been trying to figure out how we can sort of get the raw data and the software that plots these Doppler shifts and amplitudes so that we can, spread that plot out and have the same sort of timing and the,
Yes, we can help you with that.
Okay, yeah, that'd be awesome. Yeah.
And yeah, we can definitely. I'm glad you're looking at this, and it would be nice. I think you're looking only at 10 megahertz. What UTC time did the storm happen again?
Let's see. I should know this. So yeah,
18 UTC on the
17 something, 1730, I think.
And that was on May 10th?
10th, yeah.
Yeah. So which plot is that?
So that would be the second plot here, but we're already on the night, right? It's already on the night, so
The night side, yeah.
I
But
don't think.
it'd still be, well, I mean, oh yeah, you can definitely see it. Look right at 18 UTC there. It's going
Yeah, yeah.
wild.
Yeah, that's true.
yeah.
That's true. It's
Yeah,
but it's
so
not as stark as it would have been if it was right in the daylight.
it's true, but we should definitely look to see if you know, we have like data from some of the Whisper Demon Grape stations that are listening on
Yeah.
other frequencies.
Good point. Yeah.
You know,
And by the
because
way, I'll just
and
interject.
like if we go down to 5 MHz, you know,
Yeah.
2.5 or 5 MHz, you might get well actually, yeah, you're on the day side there. So
Yeah.
yeah, so actually maybe if you go up in frequency, you'd end up getting, well, we'd have to take a look, but we have, I think we probably have data with other frequencies that might
Oh,
give you a better reading.
Yeah,
And
I have all of it. I'm only showing a very little snippet here, but I have it all
yeah,
in a folder for precisely that reason. I assumed y'all would want to maybe look at that if we had
yeah,
time.
yeah. And we also, so we also have some of these stations, you know, you're only showing 10 hertz of data there. 10 hertz of, yeah, there you go.
Yeah, so here's all of it. I just picked
Okay, yeah.
one that kind of showed what was going on. But you're right. I mean, as you go to higher frequency, you see, I mean, there's just like very distinct structuring at the different frequencies. It's not entirely clear to us what sense can be made of all of it yet. But
Yeah.
oh, by the way, this is on the 8th. Wait, is this the 9th? I need to check because it's only the 10th where it's gonna. We just wanted a baseline, so we included 8th and 9th.
Yeah.
Is this the 9th? Where am I looking? Okay, let me see.
I'm really, really
Yeah.
glad you're looking at this, Jason, because no
Yeah.
one else in our team has really had a chance to look at this the way it should be looked at. So I think I'm really, really happy to see this.
Yeah, thank you. Yeah, you should definitely look at the Pennsylvania ones too, because I know that there were auroras far. I mean, there were
I
auroras
don't.
near the
I mean,
equator.
you're welcome to have our data and put it into your studies. So
Yeah, that would be
um,
amazing. Yeah.
yeah, I mean, because like I can tell you right now that I'm just I am out of bandwidth in terms of like the LSTID project I'm working on. I think Rachel
Sure.
Bodeker, she's working on the Eclipse stuff. So you know,
Yeah.
having someone who can look at this. We do have a student who's a master's student, Kung. He's a software engineering student. He can help, I think he can probably help you get a hold of the software and the data so that
Okay.
it help you with some of the plotting, because that kind of falls under what his job is. Yeah, so there I can see if you zoom in a little bit,
Yeah.
it looks like, yeah, that it looks like you've got some
Yeah.
really good stuff going on there.
Exactly. Right
Yeah.
across pretty much every frequency band with
Yeah.
distinct signatures.
Yeah.
As you said, as you go to higher frequency, it's clearer.
Yeah, yeah, this is very, very nice.
Yeah. And then look
Very
at the,
nice.
I mean, look at the 11th. My God. Just
Yeah.
crazy blackout.
Yeah. Yeah.
Look at that. I thought this one was just crazy. I mean,
Huh.
totally blacked out.
It's like all
Right.
noise.
And then you can see, yeah, here is the 12th and the 13th. It still hasn't quite recovered to normal patterns.
Yeah.
But all right. Yeah, so that's
Wow.
all
Yeah,
I've
so
got.
I'll send Kung an email and ask if he can help you out with getting that code going, and he can help get you more data, because I'd love to see this worked up into a nice study.
Tamitha, we're not hearing you, I don't think.
I just realized I didn't have my mic, the right mic chosen. Okay, may I interject? Does it mind if I?
I think I lost y'all for just a second.
Are you there, Jace?
I'm here. I missed what Nathaniel said toward the anything that was said in the last like 30 seconds or so. I totally missed.
Oh, I just said I'm gonna send my my master's student Kung an email asking him to
Okay.
help you with the data.
Yeah, that'd be great. Yeah, that's awesome. Hello, Tamitha. How are you
Hi.
doing?
I'm hanging in there. Good. Thanks for such a great presentation. I appreciate it. And I know I'm
Thanks.
not a super common attendee of these seminars, but I do pay attention. And from time to time, I happen to have a window. And this was something that's super interesting to me. And I'm sure some of you are aware, the precision agriculture folks had a horrible time back during this May 10th storm, during the Gannon storm. And they are now beginning, especially some people like Terry Griffin at Kansas University, and some other experts in the precision AG field are trying to make sense of what happened. They want to know the types of impacts. They want to know the types of, whether or not it can happen again, because both the GPS as well as the RTK system was affected. Not just from geolocation, but also, VDOP, HDOP, and of course, timing.
Yeah.
And so not only did they have problems with their guest rows, but they had problem with even having their planters dropping seed because they couldn't lock onto satellites and get timing, and they have to have timing to be able to drop their seeds. So it paralyzed the corn and soybean fields for the 2 or 3 days that it happened, and it happened in a horrible way because right prior to all of that, there was just these horrible rains, so they couldn't do any planting. And it was literally that was the last weekend they had before their insurance companies voided all sorts of coverage. So it's a total mess, and they're still reeling from it. And obviously, I don't want to hijack the meeting.
No,
But
I love it.
but what is so cool about this event is that Aurora was seen everywhere. We have tons of pictures of Aurora. We have an entire map. You guys have seen Chris Wickland's work. He's got a Google map of the G5 storm with pictures and pinpoints, locations, and it's discrete aurora with omega bands and and polar PBIs and all of the wonderful stuff that you see, plus the big SAR arcs, and he's got it all kind of populated in there. And I am so curious for those who are radio operators who love to do auroral propagation and love to see these types of disturbances. We need to consider looking at how different types of aurora, because you have diffuse aurora, you have discrete aurora, you have dynamic stuff, you have more static stuff, how this affects radio propagation at different frequencies. Because these precision AG folks, just like amateur radio operators, they have different antennas, they have different topography, they have different ground conductivity, they have different topology, right? And they're dealing with trying to get a good GDOP for those who are familiar with GPS scintillation and how to get the masking angle correct and all that stuff. They have so many issues that are so similar to the amateur radio community, but they have no experience with space weather. That I've already told a group of folks that you guys are going to be like the Elmers to the precision AG community. Yeah. And if we could somehow, I know all of us are just so stretched thin, myself included, but if we could somehow use that Gannon storm with the plethora of information across disciplines to begin kind of a super community connected, research, cross-disciplinary research, we may be able to get somewhere, at least understanding a little bit more about how these types of space weather phenomena end up impacting different frequencies all the way up to the L band. And that's one of the reasons why I was here today. So I really appreciate you letting me kind of take over for a second. Please keep that in the back of your mind when you're doing some of this research, because there's other communities and other data sets that may not be exactly what you think would be useful, but they end up being extremely useful.
Yeah. So I have been just marginally tracking the agriculture impacts too. Of course, like at West Point, a huge thing we care about is all of the different practical and infrastructure impacts, and that's one of them. I should mention that in that vein, there were geomagnetically induced currents that were very strong as well. And so that impacted the grid. And so I'm like super happy to get involved in any of that if I can provide any insights there or data or anything. But I should just since you brought stuff up, I should mention we did have the cadets watching your forecasts as this was happening. So that's kind of a cool thing, Space Weather Woman.
Oh, thank you. Appreciate it.
Yes. And also the GDOP comment. So we have one cadet now that's working on a project which sort of tries to do this, I think, very subtle and challenging task of separating out the GDOP impacts on positioning error, which just comes from, you know, the different, it's just geometry, right? From the impacts. And that further decomposes into refractive like slab ionosphere, and then more highly structured
I think we lost him there.
No, no,
Oh no. Hi, Tamitha. How are you?
I'm okay. I really wanted to hear what he had to say.
I know. Hopefully he'll come back.
He'll be back.
I'm gonna have to actually run in a minute because I have a hard stop to pick up Anthony from daycare. So if I disappear at 5
Yeah,
or
and I
in
have a
3
meeting,
minutes, that's why.
I have a meeting at 2, so I have to go too, but I am gonna be giving a talk later at West Point later this
Yep.
year. Jason
right.
is at, there you are. So I'm thinking maybe that's where I should
So am
lean
I.
is a little bit of that stuff.
Yeah,
But
Nathaniel's also invited to give a talk. Yeah.
Yeah, so I should maybe chat with this group a bit more if you guys are interested. I see some head nodding. Thank you so much. And see if we can, you know, I know everybody's so stretched thin, but if there's a way that we can exploit this across disciplines, I think it will really help us understand a bit more, because the ionosphere is just so complicated. I'm
I
so
totally
grateful to you
agree.
guys being ionospheric physicists. I don't want to be one. It's too tough.
If you are on this coast or in Pennsylvania, Tamitha, maybe you could you get a chance to stop by Scranton too. We have our new station up and running, so
Ah, cool. Yes,
it's really nice.
let's coordinate. Let's definitely coordinate. We can do that.
Yeah. Before I go, I do want to say one more thing before I go. Greg, and I'll turn it back over to Jason. Greg, VA3CBN, you're the one that gave us the TS 590 at Scranton, right?
Yes.
Well, I'm happy to report to you that finally we put it on the air,
Perfect.
and it's there's Tom using it, talking on 40 meters just last week. So we finally have the back room organized. Tom and another volunteer took care of that, and they set it up and put it on the air, and it worked great. So thank you.
You're welcome.
And we now have QSL cards now too. All right, I'll turn it back over to Gary, and I have to say 7:30 because I have to run, but I will see everyone later.
Thank you, Nathaniel.
And
Thanks,
Jason,
Nathaniel.
thank you so much for a really good talk. It's really wonderful.
Oh yeah, thank you.
I have a suggestion maybe that can explain your observation for the Doppler.
Sure.
So in a collaborative work, I am also kind of engaged in this storm. And this is the chain of ionosonde or digisonde HMF2 or FOF2 variables, how it was observed during and after the storm. So this is from 9 to 12 night. And this is when your storm or the storm happened.
Yep.
10th. So, oh no. And if you look at the FOF2 levels, the label is wrong. The FOF2 level over all the stations on the next day, which is 11, was less. And this is typically because of much of particle precipitation or dumping of the heating or the dumping of the energy at higher latitudes. We have something called disturbance dynamo, which happens much later. And that will suppress, because of neutral compositional changes, suppress the change, the electron density concentration in the ionosphere. So the overall connectivity at 10 megahertz or higher frequencies might not be achieved. They might escape to the sky or out of the ionosphere. I believe you will get much more signal connections at lower frequencies. So we go at lower frequencies because here FOF2 is almost half of the previous days. So you will have more connections at lower frequencies, and there the fluctuations or connections are more established. So this is one suggestion or comment which I can share. And one thing which I wanted to ask was, you showed one of the figures in which you had the substorm wedge or the substorm arc for
Yeah.
the whole, almost all entire South America, North America, sorry. So
Yeah.
how you get that picture? Because we have localized measurements from the images, but how you got that whole image?
Yeah, so let me, well, I think I know which one you're talking about. One second.
Yeah.
So this was straight from NOAA. So yeah, that is certainly not something that I did, but
Yeah, okay. Yeah,
yeah,
this one.
that's coming from NOAA, and I believe it's stitched together from either DMSP or some other polar orbiting, FUV detectors.
Oh,
That's
okay.
my understanding, but I'd have to look
Yeah,
again.
there's something totally new I looked actually.
Yeah, there's
You
if
see,
you're
yeah,
interested, there
yeah.
is let me just pull it up because you mentioned that. There's another one that is really quite nice from a magnetosphere ionosphere physics perspective that shows the entire oval. So
Mhm.
I
Oh,
didn't show that because this was more about like West Point specific, but it is quite a beautiful picture. So sorry for showing you all my file architecture here. Let's see, where are we? Is it this one? Yeah, there we go. Here's the polar view.
nice.
So it's beautiful.
Okay.
Right? Usually the whole oval is a smaller radius. It kind of looks like a circle, so I'm gonna say radius, but you know what I mean. Smaller radius the whole way around.
These are airglow images or density data? Particle density.
Yeah. Well, it's not density. It's definitely airglow.
Oh yeah.
I
Okay.
don't know exactly what frequency, but they may have a variety of frequencies. I think this is
Okay.
the green emission, but I could
Okay.
be wrong about that.
Okay, thanks. It looks cool.
Yeah.
Hey, Jason.
Yeah.
So down there, looking south of that ring, like there in the U.S. and the USSR and stuff like that, are those little lights or those light places? Is that also electron content that we're looking at down there, or
Oh no, this is
or is
just
that the aurora being seen, or is that just cities with the lights? What is that
exactly.
relevant?
Yeah, it's just visible light from the cities.
Okay, I was like, I didn't know if
There
if
may
it was
be a minor contribution from, some optical emissions from airglow, but for the most part, we're just seeing city structure here, which is
Okay.
another cool feature of it, I think.
And this is from a polar orbiter that is not VIIRS and SWOMI NPP data?
I'm not exactly sure. I would have to check again. I don't quote me on that.
Because it sure looks like it. It sure looks like SWOMI NPP.
You might be right. Yeah, it is FUV data, so you're probably correct. Yeah.
Okay. But yeah, it's nice to see it stitched together. Usually you see them in
Yeah.
ribbons.
Exactly. Yeah. So
Okay.
usually it looks more like the DMSP ones, which
Right.
those are polar orbiting satellites. So I think I just said the wrong thing. Yeah.
Wow, this is fantastic. You really made me think. I mean, as an amateur radio operator, I'm used to thinking about, I guess I would say, planet-sized phenomena, the ionosphere. But you took it a whole nother level from the solar system scale between us and the sun, explaining a lot of what was going on, especially the magnetosphere and stuff, Jason. So this is really thought-provoking.
Oh yeah.
Yeah,
Thank you.
Jason,
Yeah.
yeah, this was really nice. And from somebody that follows Tamitha as well and active with um, uh, her stuff, this tied in with some of her classes. In fact, she just had one on data sources. And so when you pulled up that synoptic plot, I was just like, oh yeah, I just learned about that from Tamitha. So it was a nice tie-in with some of the stuff that I've been studying with her. But I agree with Gary. This was just really well done. Thank you for your time.
Oh yeah. Thank you so much. Yep. And I love to stress the magnetospheric perspective because I mean I do think it's an underemphasized aspect. Usually you get people focusing way in close towards the ionosphere or solar wind sun stuff. but there's not a whole lot of bridging the gap in between, which I think plays a large role in all of the smaller scale structuring of things. So,
Well, if I can interject a commercial, I mean, HamSCI does have a very well-known magnetometer project, and we're, you know, ground magnetometers on Earth, Hillman, Kim, and others. And that's something that we're going to be emphasizing in 2025 is connecting what we're seeing in the Doppler shift, HF, MF regions with magnetometer data and potentially VLS stuff too. So it's, I give Nathaniel a lot of credit for having the vision to say, hey, we've got these various pieces, parts of the personal space weather station. Let's put this stuff all together and see, just as Jason was saying, how some of these systems work together or in conjunction or in opposition, I suppose they could be. So those of you who are into the citizen science, just another opportunity to contribute.
Hey, Gary.
quick
Ju- ju-
follow-up comment there, if I can. Sorry to interrupt. I don't know who was saying something. Just real quick, we have just yesterday I saw in the abridged summary the publication that came out about that magnetometer, or maybe it was 2 days ago, whatever. I sent it out to the cadets at West Point because we're all setting up a distributed network there of magnetometers, stations, receivers, etc., to do exactly that. And it's a little bit more local and small scale, but same idea, trying to integrate a bunch of different data sources to see what the actual drivers are, right? For example, ionospheric phenomena can be driven from space or from getting bumped by the atmosphere or something. So, and that's more like what Nathaniel was talking about with the TIDs. So they've learned a lot from this community. So, yeah.
Mary Lou, you had a comment?
Yeah, something I found is that beautiful aurora picture, the aurora oval, is from the visible infrared imaging radiometer suite, so VIIRS, of the Suomi NPP satellite.
Okay,
Not
yeah, I
sure
think
what
that's
that
what
means,
Tamitha
but
was
that's what
saying.
it's from.
That's what Tamitha was saying. Yeah, that's right. Yep.
It's just a beautiful
Wow.
picture, both of those. Yeah. Right.
The only caution is that you don't get such a beautiful picture in real time. And so when they've
True.
stitched that together, likely that's done through multiple passes. And so you're not seeing a snapshot of the auroral oval. Realize that just like a Carrington or a synoptic diagram of the sun, which takes 27 days to create, this takes the entire, evening to get the VIIRS, the satellite, to make enough passes that it covers the whole sky. So they're stitching it together and probably distorting a little bit of the imagery to try to make it look a little bit more even. But I don't think that this is a snapshot all at once.
Yeah, and that's a really good point because, of course, the time scale this is averaged over is much larger than the time scale of the variations of the auroral structures. So I think probably what this is a decent indicator of is the reasonable size and width of the oval, but not any of the smaller scale structuring.
Which sadly, if I chime in one last time and then I'll have to go, that will be one of the biggest challenges as we do these types of studies, is the dynamics of these, the changes in radio propagation will be on such higher time scales than a lot of the other types of data that we use that's corroborative or collaborative. And so we just need to always remember that we're so used to looking at, especially when we look at imagery, that we expect it's a single snapshot in time, and likely it will not be. It will be some kind of composite. And so time matters big time.
Could I follow up on that? Because this is another thing that actually we're working on for this very publication, but it's, of course, the most subtle part. I think the point here is there's the refractive scintillation of sort of slab ionosphere. That's relatively slow timescales. That we get fine. But in order to sample with the receiver fast enough that you uncover the diffractive scintillation from small scale structures, that's where you need to sample at above the Fresnel frequency. Toshi Nishimura, for those who know him, he published just a beautiful paper showing that when you sample at the appropriate frequency at high latitudes, you restore this supposedly absent agreement between amplitude and phase scintillation. So it was just a matter of not sampling fast enough. If you sample fast enough, the agreement's restored in accordance with theory. And so we're trying to figure out still, we have, it's actually Joanna and Colonel Laux and I are all trying to figure out, was our GPS sampling quickly enough to resolve the spatial scales and temporal scales of the structures that we saw at West Point? So more to come on that, maybe. That's a very complicated thing to determine because you need to do these power spectra and linear fits and so on, and sort of figure out where there's like this turbulent cascades, and there's two different cascade slopes for the refractive and diffractive effects. So we're trying to see if we get that, but it's a little bit hard with sparse data.
Really quickly, what is the time scale of the slab? And you said that's pretty quasi, I don't want to say stationary, but just longer time scale. What time scales are you talking about?
So it depends on latitude. Assuming that because this storm, because this storm swept the auroras to mid latitudes, I'm going to assume the same sort of numbers that you would usually get at high latitudes. It's going to be something like 1 hertz is the cutoff frequency. If you're below a hertz sampling rate, you're really just not seeing any diffraction. If you're sampling it above that, you're going to capture the diffraction. And another way to tell whether you're doing that in a more ad hoc way is just to see whether your S4 and sigma phi are proportional to each other. If they're not, then you're probably undersampling the diffractive effects.
Thank you. That helps a lot.
Yeah.
Appreciate it. All right, I'm gonna have to go, guys. Thanks so much, Jason. This has been fantastic, and thanks for some of the really cool commentary. You guys are wonderful people. I need to jump in here more.
Oh yeah,
Thanks for
thank you so
joining.
much for all the comments. Yeah, it's the best part for me is hearing everyone's nice, insightful things for me to think about afterwards. So, thank you, Tamitha.
I
Hey,
think,
Gary.
yes.
Just a real quick question, and I'll email you later. Are you looking for any magnetometers here in Utah? Because I have a friend of mine in the DX Club that's very interested and meets the criteria, and just curious if you've already got that covered.
I'm not sure. I'd have to look at the grant paper because Nathaniel
Okay,
kind of has the locations picked out. So yeah, we'll talk about email.
Yeah, we're late. I'll just send you an email. Thanks.
All right, great, Jason. Thank you very much. I mean, the thing that's one of the things that's gonna leave me after this talk is one of your initial slides when you showed the big structure coming off the sun against the Earth, the
Yep.
difference in scale, and then think about that Earth, and there are currently 8 people up there in the International Space Station going around that Earth, and what a tiny speck they are in the universe. I mean, people like Mary Lou and others who study astronomy understand this, but the rest of us, that really drives that home.
Yeah, absolutely.
Wow. Wow.
Yeah, you're playing with the big kids now.
Wow. Yeah, you're not kidding. So, all right. It is, well, thank you very much. Is there any other comments that people want to raise? I'm not sure what we've got planned for next week, but we'll come up with something good, I'm sure. We'll put our heads together. So,
Okay.
thank you, everyone. Those who are your first time you've attended, obviously, we hope you enjoyed yourself. You're welcome back. If you've got any comments, you can reach me, Gary, Alpha Foxtrot 8 Alpha on QRZ.com or HamSci@hamsci.org. So we'd love to hear your comments. So anything else, or we'll call it good night.
Good night.
That's it. Okay,
Bye-bye.
thanks, everyone.
Thank you all so
73.
much.
See you again.
Hey Gary,
Yes.
I'm sorry